Thank you. Thank you so much for the introduction. Yes. So, as Isa-Jan already said, I am a PhD candidate at TUE in the security cluster in the data protection group in the Department of Mathematics and Computer Science. Before we dive into the topic, just an introduction of my research. So what am I doing there is like designing privacy-preserving systems for unmanned aerial vehicles or autonomous vehicles, or in the context of IoT, when given scenarios like where the IoT devices are broadly generating sensitive data that needs to be shared, while we try to understand what kind of challenges arises when you integrate privacy-enhancing technologies. Yeah, so to give in most of the assumptions or scenarios where we do this is like you deploy these devices in environments where you have scarce internet connection or where you need to do safety critical operations where then those computation needs to be done on real time. And while you do this, you need to consider also the battery life. So that's why the scale of how much privacy and energy we can provide by designing a solution. Just a small part, like before I go into the storyline, for the previous research works that I've done was, for instance, as you can see here, you have a stationary mesh network and a wireless network. And for instance, you use the IEEE 802.15.4 standardization, and you want to lower the packet loss, increase the quality of service, and you want to identify interferences. So how we can do that without revealing the entire radio scheduling table, and for this we used a private set intersection. Or when you deploy drones from third-party services and you deploy collaborative policies on top of them, how we can evaluate the request so that the drone doesn't understand what kind of policy conditions are there or that been evaluated there, but still can permit access or deny access to the sensoric of the drones, for instance. So there we use two-party computation. And then also, which we are currently working on, is face recognition with drones. So where you don't want to put a reference template of the face features on top of your, like on board of the drone, because these are personal identifiable information. So how we can solve this situation while the drone can fulfill his mission. So that being said, we go further into dive in a bit more about ePPTM, which it's been available, published in IEEE IoT journal. So it's about how we can enhance privacy-preserving trajectory matching on autonomous vehicles. As I already mentioned, AVs can be seen as UAVs or submarines or even cars that have been used for various applications, so such as for goods delivery, search and rescue, or surveillance. And the idea here is we want to identify collision among the entire trajectory and not in close range, yeah? Because therefore you have the LiDAR systems to identify close range, like 200, 100 meters of collision detection. So why we are doing this is the motivation behind this that also these operator service providers can do efficient path planning as well as for safety, so you don't want to have drones crashing over you, but also to identify real-time collision detection. So in this case, the ideal way would be like we reveal your location and time data, but this may reveal customer information when the drone is delivering at what time, which location. So to prevent this, we introduce this solution. To tackle this, we have a system model where we consider two, drone A and drone B, with the preloaded time location with consecutive trajectory points. And in this case, we consider that they are assumed that they are equipped with Wi-Fi direct. So meaning like when they're in line of sight, like in range of 25, in radio visibility of 25 kilometers, that they say, okay, maybe we are collision prone. In that case, they establish a secure connection, and then we consider also the honest but curious semi-honest adversary model, where you follow the protocol flow but try to obtain more information regarding the trajectory. To give an example, if we go to Porto, that you have two drones that are delivering something, how we can understand if there is a collision over the entire trajectory before we go to the individual trajectory points. To do this, we compute or overlay the trajectory with a polygon on top of it. So how we do this is like we take the start and end point, we compute a slope, and then we compute from the intermediate trajectory points, which are perpendicular from the slope line, the max height, because this we need to compute the radius to create the capsule. And when we compute the capsule, in the radius, we consider a delta and a sigma. So the sigma in this case is the GNS as inaccuracy, and the delta is a small collision threshold that the provider is putting to compute this capsule. So, but this is done by the initiator, like from drone A. This is something I want to mention as well. And after you have the capsule, what drone A does is it wants to do a rotor translation. So it generates a random origin point. For this, it generates respectively for the X and Y axis two nonces. So it can generate this new origin point where it rotates its capsule, and afterwards it translates it to a random origin point, his entire trajectory. After this, with the new system, from the new system, it computes the capsule identifiers, which we need later on for how we can classify if there is a collision or not. Yeah, so we compute the identifier for the x-axis by taking the Euclidean distance from the start and end point plus 2 times the radius, which is for the x-axis, and for the y-axis, respectively, we take 2 times the radius with the starting point of it. So after you've done this, what happens is that the drone A sends the capsule length, the radius, the angle, and the origin point to B. So why does it send it there? Because B wants to transpose his points as well into that system. So what it does basically is it generates, from the given origin point, it generates the system, and the grids is basically with the cells inside with the size of A's capsule, but it does not know where it is. So afterwards, what then B does is from the given origin point and angle, it rotor translates his points into the system and say, okay, I overlaid this into my grid system, and then compute the identifiers which I am intersecting with in the grid system. So basically, with the previous equation that I showed you, and then in this case, we have 8 identifiers that the drone B is intersecting, and these identifiers will be then later on sent to A, and A then checks, okay, if one of them matches, then we have a collision. So this is just to give you an understanding how the plain text collision detection works. For the privacy aspect, we use a private equality testing. So what happens is after A computes the identifiers, it concatenates for the X and Y axis, the identifiers, hashes is just for a data abbreviation. And then afterwards, what it does is the Xi is just a random value. It exponents the identifier mode NB. So NB is the public key basically from B that is known to A. And then after computing the challenge, what A does is it sends the challenge with the origin, like with the capsule dimension and the origin points to B, where B then, as previously shown, rotor translates his points to compute the list of identifiers, and for each individual element in the list, it computes the inverse of it, and this will be then exponented with the given challenge. And then the result will be hashed, and then this hashed result will be sent back to the drone A. So basically what happens is like if the identifiers are the same, you have the hash of the random value. That's the main idea, which is the malleability property. And then it checks, okay, if they are equal, then yes, we have a collision. If not, then we send a random value hashed back. So this is basically the condition here. So when we have a collision appearing, then we take the nonce, concatenates with identifier, so then B does know, okay, which portion or which area am I intersecting with? And that's the main idea in the first round. So what happens is, in the first round, we want to clarify, do we have a collision or not? That's the first question we want to answer. And after that, how we can optimize this a bit. So there we introduce the incremental capsule matching. So the idea there is after we identified the collision among the trajectory, you split it basically in two individual capsules, and for each individual capsule, you do the same as in the previous slide. You compute a new system for the individual capsule, send it to B, and B says, okay, which of the portions of the trajectory am I colliding? So with this aspect, you do this until you have only a capsule size of 2 trajectory points. Why we are doing this is, so we could, best case, so from your side, on your right side, you can see that the best case is like in the first round, we compute, we have no collision, so we can move on with the mission. On the left side, on the other hand, is then when we collide, we can check in the second round which portion are we actually colliding. So if you have a trajectory points of 50 points, then you can discard basically, if the second half of the trajectory is not colliding, you can discard it, particularly the entire half away, and just focus on the other 25 trajectory points to identify collisions directly. So that's the idea with the green highlighted capsules, so that you only focus on portions, and this way we would reduce the computational overhead instead of using private equality testing on each individual trajectory points itself. Yeah, for the right one, it's just only, it says, okay, we did the computation in the first round, and we didn't identify any collision, so we don't need to move on. We don't need to traverse the tree. That was the idea. So we don't need to split the trajectory. Meanwhile, here, we identify a collision in the first round, we go further and investigate in which of the portions we are colliding. So that's the idea. So with red marked, I mean like there is no computation anymore. So that was... I hope that is clear. Yeah, okay. Yes. Yeah, that being said, we provide our algorithm in 2 modes. So, which I said first was, okay, we have no collision, no risk. The other one is the truncated mode. That means if one of the parties decides to go in the truncated mode, it showcases, okay, I reach already a tree depth where my capsule size is 2 trajectory points. Meanwhile, the other didn't reach that far. That means it could leak certain points because, for instance, B has a trajectory capsule size with 3 trajectory points, and A has 2. That means there is a false positive because in there is a third point which is not actually colliding, but this helps us to reduce the computational overhead. Meanwhile, with the full mode, you traverse the entire tree. In the worst case scenario, you traverse the entire branches of the tree, and that is a really computational overhead. But that's one of the limitations of our work here, but also one of the best cases is when you don't have a collision. As I want to say as well, after you identify a space collision, doesn't mean that you have an actual collision because you need to check also the time axis. So there we use the same approach. Like after we identify the individual portion areas, the regions, we take the trajectory points and then exactly do the private equality testing again for the time axis to identify where we actually collide in time and space. Yes, in our work, we did a security consideration, but we used ProVerif just to logically check basically our design. So in this case, we assume, also symbolically we verify it only where we assume that the crypto primitives are secure. It's not like where you can do like easy crypto or crypto verif. This is just more on the side of verifying if we did some bugs in basically when we were designing this protocol. Yeah, so and then also to identify, okay, weak secret means can we brute force basically the identifiers, or the attacker can query those identifiers, or can we distinguish between non-collision, collision if an adversary is listening on the channel. That's the non-interference. As well as we, in our work in the paper, we also gave a proof sketch on among, like, after you identify the capsules or colliding capsules, is the adversary able to guess the locations depending in the collision or in the non-collision setup. Yeah, after we did this, we did also a performance assessment of ePPTM, where we used the real-world trajectory taxi data from Porto to understand how our scheme works. So we had two test beds. One test bed was the more constrained, I would say, the Raspberry Pis who represented the AVs. And then the other more advanced commercial drones, we say, were the represented as a laptop and a standalone PC. So where you can see here in the collision aspect, so around 90% of our collisions are less than 10 seconds. But then we had some cases where it was like 18 seconds, and that's what I already mentioned. That's one of the limitations when the trajectories are strongly overlapping, then you have to traverse the entire tree, which increases the computational overhead. But this is also depending on the relation between the trajectories, which you don't know beforehand. Yes, so this is so part for the performance assessment. To conclude and future work aspects, so we presented here in our work a spatiotemporal trajectory matching on autonomous vehicles with the incremental capsule matching that allows us to give up trade-off for the computational overhead, to reduce that with privacy-preserving proximity testing. And as you can see, also one other limitation is right now on the two parties. The question is also appearing on how we can scale that for multi-party trajectory collision avoidance. So yeah, thank you. Maybe do you mind if I can present also the research trajectory for the future? Yeah, okay. So yeah, there is just a small aspect. So when we can still take the scenario for the detection of malicious input, like how we can guarantee that the trajectories that we are inputting is actually the trajectories that we are providing to you. So maybe there is a way of using a zero-knowledge proof based on the capsule computation related to your trajectories that you maybe guarantee input verifiability. So that was one idea. And also in the first slide, when I showed you the previous works where we used two-party computation, so in case of the policies, when you have the policy size, for instance, is represented as the circuit size that the drone needs to evaluate. So if you cannot optimize that part, we were thinking on using either input verification with verifiable secret sharing so that the drone doesn't waste too much on its computation over a corrupted input. So that was an idea of having a trade-off. Also, the other part was the memory footprint. So when you have a lot of, obviously it is clear, a lot of NCADEs, if it scales, you have a lot of triples, or depending if you're in Boolean circuit, the multiplication triples, or in the arithmetic, the beaver triples. So that aspect, how we can reduce this. So there was an idea maybe to use the silent OT extension that you say, okay, we have a seed pre-shared on the devices, and later on when they are doing the online evaluation of those circuits, they can expand it, the necessary values that they need for evaluating the online phase. So these are some ideas for future research trajectory, and I'm open for input and feedback. So yeah, thank you so much.